Yeah, let's wait a couple of minutes and then we will start. Yeah, first I think we'll go over the standards, just discuss the abstract part, like the motivation, go into the implementation details, some problems with the standards. Yeah, if you have any questions, you can just interrupt me at any time. And after that, I prepared a quick integration with the registry, and yeah, I will show you how to do it. It's Solidity plus Circom stack. Yeah, well, I'll show you. So yeah, it's go time. I will share my screen. Yep. So yeah, the standard. We decided to write the standard because we see that there are a lot of like stuff going on in the ZK identity space, and it seems like everyone is working in their own niche, and it's hard, to collaborate on something and to like, converge this effort into like one flow and to make something that everyone could benefit, to make something that is useful, like a useful building block where everything can be built on top of it. So yeah, we gathered with the Rarimo guys, with the ZK Passport guys, and the Dario Buterin, and decided to write like this building block. This is not the final point where we think the ZK identity will go. This is more like the base, the foundation, where I mean, you can build sort of different standards on top of this standard. For example, one for passports, one for some social graphs, another one for some ZK attestations, and they could all like be built on top of the standard that we propose. So the abstract part, basically our system is really simple if you worked with ZK before, but this is something that no one has done before, because we propose the like single single registry where everyone can integrate with. It is permissionless, so no one has direct like control over this this registry. So it's deployed, available as a singleton smart contract, and it is just there for public good. So none of the authors, no one can like modify the code, no one can modify the behavior of this smart contract. It is important to know that the proposal is still in draft, and it's likely that we'll change some functions, some behavior of the registry, and thus the address will be different because we'll have to like redeploy it. This is something to note, but nevertheless, you can just take a look at what is deployed and start integrating already. Just feel how to do it. Yep. In terms of specification, we are using pretty much de facto the standard of ZK, which is the sparse Merkle tree. sparse Merkle tree is a really cool data structure that is deterministic. It is deterministic in a way that if you add the same elements into the data structure, it will give you the same sort of root. And we are using the custom implementation of this data structure, which is like super optimized. The standard uses this implementation that we like tested, like paddle tested. It's fast tested. It's super robust, and we tried to make it sort of as efficient as it gets, not going into some crazy assembly. Yeah, we can also discuss how this sparse Merkle tree works if you want. We are also using the Poseidon hash function, which is sort of the optimal, I would say, hash function currently to be used in zero knowledge. So it's very efficient. It's really easy to be proved. One note that the Poseidon hash function is still considered not safe. So there is still an ongoing bug bounty over for Poseidon, and even Ethereum Foundation like leads this bug bounty, and there is still a possibility that this hash function is not safe and may be broken, but currently it's considered like the standard in the ZK space. Yeah. So what the standard actually proposes is we have like a central registry, which is permissionless, deterministically deployable, and this registry uses the sparse Merkle tree sort of database, and the standard actually it doesn't enforce certain data structures, doesn't enforce certain structures at all. It only enforces the interface to be followed, and then, for example, if there is a breakthrough in zero knowledge, and that someone finds new hash function or someone finds a more efficient data structure than sparse Merkle tree, then they can deploy the new representation and just follow the same interface and still be like compatible with the standard. So these are two main smart contracts. The evidence registry acts as an entry point to the system. So every sort of write to this database will be made through the evidence registry. And for example, if you need to get the root of the tree, or if you need to get the Merkle proof for the tree, you'll go into the evidence database and call it instead. The cool part of the system is that it allows for easy integration for custom business use cases. I call it registrars. So you can implement passport register, social graph register, some simple register, custom register, and then easily access the shared registry. There are some issues with that, and the standard solves them. So one of the issues is because the state is shared, we somehow have to divide the tree, like the underlying database, the underlying tree, between those individual registrars, because otherwise, social graph can add something to passports, or passports can delete something from social graph. So this is not really cool. So that's why there is a mechanism that prevents this from happening. And basically, yeah, business logic is delegated to the registrars. If you're building an app, you're building some ZK identity solution, you will build the registrar, implement your business logic there, and then use the evidence registry as a shared, like, provable database. So that's the idea. Yeah, the quick description how it works. And here is the interface, the evidence database interface that the database has to follow. So it means that you can use not only like sparse Merkle trees, you can use whatever you want as long as it's compatible with the interface. And also the interface for the evidence registry. Yeah, it only has to support 4 functions, which is really easy to do. Yep. This part, the isolation. So this is what I said previously. So this basically separates the tree from one registrar of another registrar, and the message sender here is the registrar, and the key is whatever the user wants to add into the registry. So we have to isolate different business logics. So instead of just placing the user key directly into the registry, we isolate it with the integration message sender, and then basically it's impossible for different user to like modify, not their part of the tree. This has some constraints on how to integrate with the registry, but yeah, I will show it when we go into the integration part. Yeah, the hash function. Yeah, the standard, as I've said also earlier, it doesn't enforce any hash function. You can use whatever you want. But yeah, we are using Poseidon, and it is very important to check that the values are not bigger than the scalar field size of the BN curve. With the new fork of Ethereum, there will be new curve added, so it's possible to implement this register in a new curve, so there will be a new value. But yeah, it's important to do this check, because otherwise there may be some nasty collisions due to overflow and modulus. The rational parts. So it may be really hard to find like what benefits exactly does this proposal propose. I can list several. The first one is, of course, the shared state. So it's like a permissionless shared state, which is provable. Currently, it is very hard to prove Ethereum state. So there is work going on how to make like Ethereum ZK provable. There is even a new proposal which like proposes to migrate the Merkle Patricia tree to a different one, like a sparse tree, which will be provable in ZK, but this is only like in a pre-draft state. So, but we want the provability right now, and pretty much the only option is to have this probability on chain, not like on an infrastructure level. The second one is cross-chain portability. So because we are using the sparse Merkle tree as our registry, so the whole state basically can be represented as one byte 32 value, the root of this tree. And if you need, or if you want to prove that something exists in this tree, you just only need to make sure that your root is one of the roots that existed in the original registry. So to make cross-chain portability, you just need to transfer one byte 32 value from the registry to other chains, and that's pretty much it. Then you can verify proofs against this root, and this is really easy. So no need to transfer the whole tree. You just transfer the root. The second one is a lot of projects are using their own sort of registries, which are based on different data structures, like incremental Merkle tree, similar sparse Merkle trees, or just regular Merkle trees that they then prove. But this is they're project based, and another different project can't necessarily integrate with their building blocks. That's why this standard is the public good that can be used by anyone who wants to be sure that there is no single entity who can just wipe everything out, because the registry is permissionless, immutable, so no one can upgrade it, no one can downgrade it. Only the certain business registrars that integrate with it, they can modify some data, but you can design a system on top of this registry that is also fully permissionless and available to everyone. And also the integration. So because it is all formally written and it won't change significantly, you can build certain public good libraries, public good tools that will just allow developers to integrate seamlessly and easily with the standard, and you can be sure that it will all work fine. Yep. The AP is fully backwards compatible. I'm actually looking forward to the progress on natively provable Ethereum state, because this will allow basically the same experience, but natively with mappings, natively with just storage variables, and you won't need to use a special data structure for provability, because everything will be provable in Ethereum natively. So regarding the deployment method, this is a really fun part, because we wanted to achieve a really nice address. So we wanted to compute a cool address for our registry, and we did it. So the address starts with 7812 and also ends with 7812. So it's really hard to confuse this registry with something else. And it was actually a bit hard to find the correct salt to deploy it properly, because under the hoods, we are using Poseidon hash functions, and those Poseidon hash functions are libraries. We had to deploy those libraries deterministically. We had to like relink in the low-level bytecode manually those libraries. We had to compute them the salt, which took some time, and finally deploy it. So this deployment method, this process, is fully written as a script in the reference implementation of the standard. So you can take a look at the script and just run it on any EVM network, as long as you have the deployment, deterministic deployment factory available. And yeah, it will just deploy the registry right away on any EVM network you want. We also made sure that the registry in the reference implementation is compiled with like lower EVM targets, because newer targets like Shanghai, I believe, and Paris, they are not like fully available on some L2s, especially on some EZK L2s. So yeah, we compiled it with London target, and it basically means that you can deploy it, I believe, on pretty much any EVM network you want. Yeah. The reference implementation, I will show it a bit later. Yeah, here is the EvidenceDB implementation. Yeah, because the standard is still in draft, I think we will eventually change some interfaces once we start integrating with the standards on some projects. And also, yeah, I just encourage everyone to take a look at what is currently available, and if there are any concerns or any thoughts how to improve it, then of course I will be happy to reply and to collaborate. Yeah, the evidence registry implementation. And we also have the verifier reference implementation. This is a circuit written in Circom that basically allows this state of the registry to be proven in zero knowledge. In the integration thing I will be showing after this circuit will be used to prove that we know the image of some hash that is added into the registry. So this one, yeah, like is also battle tested and can be used everywhere you want. The one part that worth noting is this 80 number, which is the height of our tree. Yep, in the reference implementation part, it's noted here that the registry is deployed with the tree height of 18. So this means that no more than 2 to the power of 18 elements can be added into the tree, but on practice that is actually even less due to the sparse Merkle tree internal like data structure. And in practice, I think it's so you will likely hit a collision with 2 to the power of 63 something elements. But yeah, 2 to the power of 63 is like mind-blowingly large number, and it's basically impossible to reach it in our lifetimes. This is something worth noting, because it's like a limitation, I would say. Yep. And the security considerations. I think the most important one is when you're integrating with the registry, it is important to properly understand how to check the root validity of the registry. And that's why there is a function for that called get root timestamp. And what it basically does is that it, instead of returning you the latest root of the tree representation of the state, it returns the timestamp of the root you ask. Because this get root method that just returns the latest root, it creates a front-running possibility. So whenever the user updates the registry state, there will be a new root. And for example, a different user just generated a ZK proof that's committed to the latest root. Then the root changed, and the user just won't be able to prove anything because of the new root. So their ZK proof will be just invalid. So that's why the correct integration would be to just call the root function of chain, get the root, and then generate the ZK proof based on the root you obtained, and then provide this root as a parameter to the function. Because this will just eliminate the front-running possibility, and then draw use cases where you can get the timestamp of this root, say that, okay, we only accept roots that are not that are only 1 day old or 1 hour old, and the older roots are discarded. So as you can see, this is not a super complicated standard as of now, and it's not designed sort of to be complicated, and it's not designed to solve particular problems, but it's designed to be able to build on top of it and write proposals that will reference this proposal, and you can have the password system built on top of this. You can write your own EAP just for passwords, and etc. etc. Yep. So this is the quick intro about the standard. If you have any questions, please ask. And after that, we'll go into the integration part. Okay. So the actual sort of workshop part of this presentation is how to actually build something useful on top of the registry, how to integrate with it, and what problems can you face. So I've prepared a very simple registrar that allows everyone to add some hash to the tree, to the registry. So this can be like any hash of whatever the user wants. And then there is a function to check that the user knows the pre-image of hash that is in the registry. So you can think of it as we are just proving some private data that the user knows exists in the registry. Yeah, as simple as that. Our smart contract, it accepts the registry and it accepts the ZK snark verifier smart contract. Yeah, add function that just calls the registry, add statement, and provides this hash as a key and the hash as a value. So under the hood, the registry, it will check that those values are in, within the scalar field size, and it will build the isolation for our key. So the isolation is basically the Poseidon hash of the message sender. This is our registrar, and the key the user provides. And in this form, the isolated key will be added into the sparse Merkle tree, and the value will also be added into the sparse Merkle tree. The verify function, it accepts the ROS16 proof. So this is the struct, A point, B point, and C point. The ROS16 proof. It accepts the registry root. The thing I was talking previously, that you have to pass this value as a parameter, because otherwise there's a front-running possibility that the root updates, and if you call the registry get root function on chain, it will be different, and the proof will fail. So instead, you will pass it as a parameter, and then call the registry to check if this root is any valid. So because this is a very simple registrar, we'll just check that it exists. So the timestamp returned by the registry is not 0. Then we'll build an array of public signals for our ZK proof. So of course this will be the registry root. This is the public commitment that we need to prove. Then we'll add the address of our registry for the safety purposes, because if we are not adding this address here, basically someone may deploy their own registrar and add some hash there, through their registry. Then we'll prove that the hash exists in the tree, but we won't prove that it was added through our business logic. It was added from somewhere else, which is not cool. And also the additional public signal is AUS. So this is an address that we would like to authenticate. Because without this address, if I see that there is a proof submitted on chain, I can just copy it and send my own transaction with the already existing proof. And for example, prove that I know the pre-image, of some hash in the tree. But in reality, I just copied the zero-knowledge proof and I don't know the pre-image. That's why whoever knows the actual pre-image, they will provide some OS address here. Usually this would be themselves. And then the proof, the zero-knowledge proof, can't be like replicated, because you'll need to change the public parameter, and proof like won't work if you change this. So those two public values are just security thing, and the first one is like requirement, absolute requirement, and the last line is we will call the snark verification function on our verifier. We'll provide public signals there, and we'll provide our points. So if snark verification is fine, then we proved that we know the pre-image of some hash which exists in the tree. I'll show you the circuit in a second. But yeah, currently there is no like objection to prove the exact hash of something. We just want to know that user knows pre-image of some hash that exists in the tree. Yep, here is the simple circom circuit that proves this. So we are including the circuit from the standard. This one is literally in the EAP. We'll be integrating with it. So here we provide the levels value, which is 80 in our case, the height of the tree. We have the signal roots, signal registrar. This one is needed for isolation key build. And we also have an AUS input. It doesn't have any constraints, as you can see. It's just a public input for like to make those ZK proofs sort of bound to certain authentication address. So you won't be able to change it. If you want to change it, then you have to regenerate the proof. Then we have as an input our pre-image. We have as an input the sparse Merkle tree siblings. And what it does, it just creates a registry component. We calculate the hash of our pre-image we want to prove we know. This will be our key, which we add into the registry. And then we just forward it to the registry itself. So under the hood, the registry circuit will hash it once again with the registrar to build an isolation key, and then the circuit will go over the sparse Merkle tree logic, and it will build the roots inside the circuit based on the siblings that we provide, and based on the key we are trying to prove. Those values are left as blank because sparse Merkle tree allows for inclusion and exclusion proofs. You can prove that there is something that's not present in the registry because sparse Merkle tree is deterministic. But in our case, we can just leave them blank and it will be fine. And of course, we're providing the root here. Under the hood, there is a constraint that checks that the root that we provided equals the root obtained from within the circuit from siblings and the key we provided. The public signals of the circuits are root, register, and authentication address. So the pre-image is private, and siblings is also a private signal. Yep, let's then compile it. Yeah, actually, I'm using a plugin to compile this thing, the circom circuits. So, yeah, first of all, I will need to run a local node. So just to showcase that the registry works and this whole integration, yeah, there are two options actually. The first option is to like run this on Sepolia or on mainnet. The other one is to fork Sepolia, and the third one is just to run a local node, deterministically deploy the registry here, and just test everything locally. So I'll be using the third option. So just running the local nodes through Hardhat. Then I will deploy the registry to the local host. So yeah, it's deployed deterministically the registry to the same address, and the database has also the same address. So we can confirm it by those transactions appearing in our local node. And yeah, we are ready to, we have our environment ready to test the integration. So yeah, first thing I need to compile our circuits. So circom is a really complex thing. So we first need to compile the circuit into R1CS representation, have the witness calculated. Then we'll need to use the snark.js to build our proof. We need a trusted setup. We need a lot of things to worry about. But yeah, I'll be using the plugin that just makes life easier. So it's one line of code, and we are ready. Yeah. So it says nothing to set up just because I've set up the circuits earlier, but we now have the build circuit, we have Z keys, we have everything. Then I need to generate the verifier for our zero knowledge to work. So I'll be using the same plugin to generate the verifier. Yep. So verifier is generated. There is this one. Then I need to compile the smart contracts. So compile the smart contracts, and then we can test the integration. So here is the test I will be running. Let's just quickly go over what's going on here. So there are two addresses from the EAP, the deterministically deployed ones. Here is the secret. So this is the pre-image I will be proving. So I will first add the hash of this value to the registry, and then I will prove that I know the pre-image of this 1337 value. So first I need to deploy our register, our simple register. So here is the verifier, here is the registrar, here I'm deploying the verifier, here I'm deploying the registrar. We also need to provide the registry address in the constructor. Then I'm calculating the Poseidon hash of our secret, and I'm calling the function to add this hash into the registrar. Then I need to get the sparse Merkle tree proof of this hash that it exists in the registry. So that's why I need to build an isolation key like on the front end. So that's why I'm using the Poseidon hash 2. So I'm taking the register address, and I'm taking my key, which is a hash of secret. And this will be our isolated key that is added into the registry directly. Then I'm obtaining the sparse Merkle tree proof. I'm calling the function on the evidence DB to get the proof. And then I'm starting to use the plugin. So I'm getting this circuit, this one, simple register circuit. I'm getting the signer, will be an authentication, the third public signal. Yep, this one. This one is our signer. Getting the signer from Answers. And then I am generating the proof. So I need to provide the root, of course. I need to provide the registrar address. So because, yeah, we are working with zero knowledge and everything has to be converted into numbers, so I'm converting it to begins. I'm providing the authentication address, and I'm also providing the pre-image of our secret and siblings, also by converting them to begins. Then, yeah, so this generates the proof. I'm getting the proof. Then, because proof has some extra data that you don't usually need to be like passed on chain, I'm generating just the bare minimum from this proof to get the actual callable call data. And then I'm calling the verify pre-image function. I pass all the points here from call data, and also pass the root publicly, and signer is our auth thing publicly. So because the environment has the singleton registry deployed, the integration should work. I should add the hash, and then I should be able to prove that the hash exists. So, yep, I need to do APX hard hat test on network localhost. And you can see that test is passing. This means that the hash was added and the proof was proved. We can, I don't know, play with it and let's say pass different values for the proof just to check that it's not like super optimistic. Yeah, so here you can tell that the proof is invalid. Let's do, instead of passing secret here, let's try to pass, just 1, 2, 3. So let's see what it does. So it says that I can't generate proof. zero knowledge proof for that, because the witness doesn't, so it can't get the root. It can't get all the constraints to pass for the root to match with our root and with the hash that we are passing. Yep. So actually there is one issue here with the registrar that I haven't mentioned. So this issue is not like super critical, but still, because we don't have any like nonce here, we can still reuse this proof with our OS address. And for example, if user verifies their pre-image once, like anyone can send just the exact proof and with exact parameters and call this function, and it will still pass. So ideally, you would need some nonce to just block the reusage of zero knowledge proofs. You can, for example, calculate the hash of the points, but this is not like super secure. This is considered really not nice practice. This is the same as using the hash of the signature as the nonce. So ideally, you would need to build some mapping that maps into a OS and some value, and then you will use this value, like the nonce, to be passed into the proof as a like public input, and then you will increment this nonce so that the zero knowledge proof can be reused. This is one thing to worry about. For the purposes of workshop, I didn't do that, but this is a very important security concern to address if you want to integrate with the registry properly. Yep. So what I can add here is that we are working on full big integration with the registry right now. So there will be like a huge application that relies on the registry and relies on the standard. Probably we will find some like missing links, some not really nice integration points, and update the standards. And yeah, this will mean that the address will be different for the registry. But yeah, this will be certainly reflected on the forum, and it won't be missed. Okay. That's actually it's what I planned for today. If you want to discuss anything, or if you have any questions, like how can I Yeah.
Yeah, it worked. Thank you.
Let me add everyone. Yeah.
Thank you, first of all, for the presentation and great work. I have a few questions. One is regarding maybe you can give an example of real usage for the registry, like what use cases could be covered. As I now understood is that, for example, you could prove that you know secret that is in the registry, yeah, but and that's all that you can do with it right now. So if you want to do something else, then you would need to write another circuit, right? And also, yeah. So yeah, maybe you can describe what exactly are you going to do with it, if it's possible.
Yeah. So we will write like a separate registrar for passports use case. Yeah, we are currently working on Rarimo to allow that. So it's already works, but it works with like a different architecture, and we will sort of migrate to the registry. It will be like open to everyone to integrate and to use. The thing with passports is that I think there will be several actually registrars to support this use case, because there is like a layer of certificate issuance, there is a layer of passports issuance, and technically, for example, one project can just support the certificates issuance and add them into the tree through some, standard in a standard way. And there may be a different project that uses those certificates to check the validity of passports. But yeah, for this to work, we need to develop a registrar. We need to develop a circuit to prove that, for example, if we add like the hash of the passport into the registry, we need a circuit that would reconstruct this hash. Probably several circuits because of the complexity. Yeah, this is what we are currently working on. But yeah, in terms of like workshop, I didn't want to have this huge complex thing explained just a really really simple like pre-image. Yeah.
Mm-hmm. Yeah, thank you. So am I understanding this correctly, is that so this proposal is giving an interface for the registry itself, but is not giving how to use registry. So on the usage side, it should be kind of different circuits that would be consuming data from the registry, right? And then on the writing side to the registry, you are also not constraining what data and how should get into it. So in case of the passport, let's say, it would be another ZK circuit maybe, or something else that would be verifying that person is inserting data actually, let's say, owns it and it's valid, right? And then, yeah, he would be able to use it.
Yeah, that's what I was talking about, is that you can certainly write your own like improvement proposal just for passports use case and describe that, okay, we need to manage data like that, we need to manage certificates like that, we need to hash them like that, we need to do this, and just say that, okay, we need to store it somewhere, but where do we need to store it? And here is the proposal that solves the storage problem. So it doesn't necessarily solve the use case problem, but yeah, it's like the first, step to like progress somewhere.
Okay. One more idea is that, like, a small improvement proposal is that maybe instead of using address as a Ethereum address, because if you're using Ethereum address as an kind of identity of the person, then whenever a person needs to prove something about the registry, then he would need to reveal his Ethereum address, right?
Yeah.
So maybe it's just a small improvement that you could do is that you could accept any kind of hash or identifier from registrar instead of just relying on Ethereum address. Then it would be possible to instead of address use, let's say, public key or like hash of baby jab key, or identity or something else, like maybe hash of a secret that then later user would be able to prove control over it, something like that.
Yeah. Actually, with our passport use case, we are using the baby jab key pair, so it's not like the Ethereum address. Yep.
Okay. Great.
Thanks.
Thank you. Yeah, that's it from my side.
Can I go next?
Yeah, please.
Yeah. Thanks a lot. Yeah, it was very, very interesting. Okay, I have a couple of questions here. I will try to keep it very shortly, but I would like to understand who and how will benefit and which levels, from the system. First of all, as far understood, this, let's say, contract, will be act as the database with isolated tenants. So every registrar will have the isolated, let's say, area, and all identities will be stored there. So they will not overlap. So for example, I have two registrar. I register in one, register in another. It will be two records inside this contract. So super. Second question. Will, let's say, real life business will benefit? For example, I have some retail store or whatever. I already have my digital identity in AWS Cognito or whatever. What? How I will benefit if I will replicate it inside this contract? I already have authentication, multi-factor authentication, or whatever. And after that, without any issues, I can integrate it with Ethereum. And put their identity. Why should I do it? Do you have any ideas? For example, why should I do as a business owner? Or this is just for smart contracts era. And for example, if I'm developing some distributed autonomous organization, I will definitely use it for whatever reasons. If I real business from outside, how can I use this zero knowledge proof? To do what? To prove what? Or who can use it? I just want to understand.
I think if you're like a centralized company, like consolidated company, then there is no real benefit. So because you already like own the data that users provide to you, like KYC, whatever. But if there is like some project that wants to be like a really cypherpunk project that believes that only decentralization wins in the long term, that identity is something that belongs like to you, not to some centralized whatever, then they can use the standards.
Sorry for interruption, but in your case, registrar is also a single point of truth, because you said that it will be contract, fully isolated. I can do whatever I want. I can add entity, remove entity, identity, from our system. It's still some kind of centralized control, inside my registrar. I can do whatever I want. So again, there is no big difference between AWS Cognito, for example, or Okta or whatever, and this registrar. Yeah. So yes, again, I'm just thinking, and also again, was a question about B2B user. Yeah, I am retail store or whatever. Yeah, but how, let's say, B2C user will benefit? Let's say I am logging, I am registered. This in some sense it was inserted into the system, and as far as understood, after that I can, let's say, with using the zero knowledge proof, answer that I am part of this registrar, yeah, without revealing any information about myself. Yeah, for example, yeah, let's say Amazon integrated with this system, yeah, and after that I can, for whatever reasons, for whatever who asked me, I can say okay, but without revealing my email address or whatever, yeah, and I can say I am registered in this system, yeah, and this is a big difference between, again, some centralized exchange or business, or something developed or inside Ethereum network. Is it correct? Yeah. So
yeah. So if there is a registrar, for example, passports registrar, that's like you are sure that whatever data is added there is from like your password. It's so you are not revealing your password, but you're sure that the zero knowledge proof will say that your like passport data is this. And for example, if you need some KYC, you can just generate the zero knowledge proof. Say that, okay, I am 18 years old at least, and you won't
all the benefits from zero knowledge proof. Yeah. And again, maybe this will be some kind of top, but I didn't check it for a while, sometimes, but I know that Cardano, they are heavily working in this domain, yeah, and they are building some country in Africa, I believe, something based on some digital identity, yeah. Have you checked maybe already existing project about the digital identity, because this is super cool area and super complex area, yeah. Maybe you can share with me some information, because I have not had a chance to check it.
Yeah. So I'm working on this protocol. Rarimo, Alexander is working on IDEN3 protocol. Yeah, which is basically the like different approaches to digital identity. There is a WorldCoin with the semaphore under the hood. What else? Yeah. So these ones I did check, but probably not for Cardano.
Yeah. Okay. Yeah. Thanks a lot. Again, yeah. By the way, it's very interesting. Yeah, I can just send you an invite in LinkedIn, because it's very great. Because I have a couple of ideas how to implement it. Yeah, maybe we can keep in touch and maybe discuss a couple of ideas.
Yeah. Go on, please.
Yeah. Thanks. That's all from my side. Thank you.
Yeah. So,
can I go next?
Yeah, of course.
Yeah, Artem, thank you for the presentation and for this great job that your team done. It's really cool. Yeah, my question is that if I understand correctly, the logic of the verification and the structure that you use specifically Poseidon hash at the moment. Yeah, it's clear, because you need to use zero knowledge, which is based on circumference. It's a limitation. But if you imagine that in the future, the key technology evolve and other hashes would be possible, yeah, then that might be a problem that you are kind of rigid. You are very coupled to this specific hash.
Yeah,
we're thinking about a way to introduce deep sparse Merkle trees or even other kind of Merkle trees in the future, but still not to make it to deploy to another contract with another entry point. So introducing another entry point for the industry and for all the clients who use your system. So maybe you were thinking about a way to add a new hash algorithm index to the isolation key calculation. Or maybe you're thinking about adding in the future some Merkle structures on top of many Merkle structures that each we use in different hashing algorithms. So what are your thoughts about it?
Yeah. Actually, we had like a lot of like internal discussions, even with Vitaly Buterin, had a discussion how to properly present the standard, because it's really hard to somehow like write something useful in this area, because it's like super progressive, and it's hard to find some point that can be like organized and used for some collaborative efforts. We had an idea initially to have some registry as like a router. So if we are talking about Uniswap terms, there are like trading players, which are different projects building something. And initially we thought that it would be cool to have some router that would aggregate them and like use many trees under some conditions. But it was really hard to like formulate how to do it. So then we decided to, okay, let's have a tree, just one tree. And if you need more trees, you can just write them in your own registrars. You can have your own registry, your registrar, whatever data structure you want. You can have subtrees of subtrees, and then just push the root into the main registrar. So this way, scalability may be achieved. In terms of Poseidon hash function, so yeah. I don't think that we will have some super major breakthrough in this, like in the near future. I think we'll have some improvements in terms of new proving system, new possibilities for zero knowledge, etc. And that's, I know, Ketchak proving would be easy, but it's hard to beat Poseidon, like really hard to beat Poseidon. It's like it's just designed for zero knowledge. And we like deliberately decided to make it permissionless and like non-ownable, non-DAO ownable, nothing. Because like this is the only way the standard may work. You can deploy it, I know, on, for example, you're launching your own ZK rollup. You can have your own registry which follows this like interface, but also has like upgradable functionality through the DAO. But for Ethereum proposal, it just doesn't work this way. So it has to be permissionless and ownable. This is just a limitation we have to accept.
Yeah, that's clear. Thank you.
Okay. If there are no questions, then I think we can call it a day. Of course, check out the standard yourself. In the Ethereum proposals page, there is a link to Magicians Forum where you can leave all your suggestions. We can, discuss it in more details and like collaborate how to make it better and more usable and cooler. So yeah, I highly encourage you to just take a look and leave some feedback on the Magicians Forum. All right. So thanks everyone for attending. Yeah. Bye.
Thank you a lot. Bye.
Thanks a lot.